Hey everyone, welcome back. This is Engineer Hussein Mwasapi. So in this video, we'll be looking at what is known as Laplace transformation, or others could term them to be Laplace transformers. So before we begin, do not forget to like and subscribe to the channel. All right, let's get to it. So how can you define Laplace transformers? So by definition, Laplace transformation is basically the process of taking the f of t, which is the t domain, and transforming it into the f of s, which is the s domain. Therefore, if we have such a statement given, it implies that the f of s domain is equivalent to the integral from 0 to infinity of e to the minus st of f of t dt. This is the Laplace definition. In the definition, I want you to understand that f of s is the Laplace domain, which is basically the s domain. Then f of t is the function of t, which is the t domain. If you want, you can say that f of s is the function of s, which is the Laplace domain, and f of t is the function of t, which is just the t domain. So be mindful that the Laplace transformation is the process of taking the f of t, which is the t domain, and transforming it into the f of s, which is the s domain. And this is the definition. With this said, I want us now to look at the proofs we can have under Laplace transformation. All right, now let us look at the Laplace proofs. To start with, we'll start with the Laplace of k, where k is a constant, which is any number you can think of. The Laplace of the constant k is equal to the constant over s. This is your answer. But we now need to understand how we can prove this. So let's look at the proof. We know that by definition, the Laplace, which is given by the f of s, which is the s domain, is equal to the integral from 0 to infinity of e to the minus st of f of t, which is the t domain, dt. In our case, f of t is equal to k. So the s domain will be equal to the integral from 0 to infinity of e to the minus st of k dt. Now, since k is a constant, we know by the properties of integration, the k can be pulled out. And we have f of s being equal to k, the integral from 0 to infinity of e to the minus st dt. The integral of e to the minus st is going to be, we'll have k, and we'll have the same thing. Remember, if we're integrating e to the something dt, this is always e to the something over the derivative of something, then plus the constant of integration. But in this case here, we'll say that we'll have e to the minus st over the derivative of the something, which is minus s. Now, since we're taking the limit of 0 to infinity, the constant of integration will not be considered, and we'll have it from 0 to positive infinity. By substituting this, we'll have a case where we have the f of s domain is equal to a case where we'll have k, then we'll have a substitute where we have e to the minus infinity then s over minus s, then we'll have minus with the minus makes the plus, but let me just write the minus for the sake of accuracy. So e to the 0 over s, because when s multiplies 0, we just can end up having a 0 in the end. So the f of s is now going to be k. We know that e to the negative infinity will give us 0. So we have k, then this would be 0, minus minus gives us a plus, and we'll have 1 over s. This tells us to say that we have k over s. Therefore, the Laplace of k is k over s. And we have proven. Let's move on to the next proof. Second proof will be the Laplace of t to the n. Now, I need you to understand that the Laplace of t to the n is equal to n factorial over s to the n plus 1. Now, how can you prove this? Let's see its proof. We know by definition that the s domain is equal to the integral from 0 to infinity of e to the minus st of the t domain f of t dt, where in this context, f of t is equal to t to the n. So the s domain, which is equal to the integral from 0 to infinity of e to the minus st of f of t, which is t to the n dt, will be solved, or proved rather, by using what is known as gamma substitution. Now, under gamma substitution, we'll let x be equal to st, and we'll let t be equal to x over s. We'll then find the first derivative of x with respect to t, so dx over dt will then be s. Then we'll make dt the subject of the formula. Now, since dt and s are inversely related, we'll have dt being equal to dx over s. Now, from the s domain, f of s being equal to the integral from 0 to infinity of e to the minus st of t to the n dt. By substituting what we found, or what we've used in a gamma substitution, it implies that the s domain, f of s, is now equal to the integral from 0 to infinity of e. Remember that x is equal to st, so we'll have negative x. Then remember t is equal to this, so t is x over s to the power n, and dt is now equal to dx over s. Now, we're going to apply basic algebra. So the s domain is now equal to, if we pull out all the values that we feel like are constant, not that we feel that are constant, we'll be having a case where we first have to now simplify this portion here, where we're having e to the minus x, then the n will be distributed to x and s, where we're going to have x to the n over s to the n, and then we'll have the x over s. Now, we know by remembering indices, we know that s to the n times s to the 1, this gives us s to the n plus 1. Therefore, the s domain, f of s, is equal to the integral from 0 to infinity of e to the minus x of, what are we going to have now? If we apply this in context, we'll have x to the n over s to the n plus 1 dt, dx, sorry. Then the s domain, f of s, is now going to be 1. If we pull out this portion here, which is the constant, we'll have s to the n plus 1. And we remain with the remaining portion, which will be the integral from 0 to infinity of e to the minus x times x to the n dx. Now, this portion that we remain with here is called gamma. This is gamma. So the gamma of 0 to infinity of e to the minus x of x to the n dx is equal to n plus 1. And that is if n is an integer. So if n is an integer, so we say if n is equal to an integer, then what does it imply? It implies that the n plus 1 is equal to n factorial. This implies that the S domain is equal to 1 over s to the n plus 1 times n factorial. And this will give us n factorial over s to the n plus 1. And this is our proof. So in our third proof, we're finding the Laplace of e to the t. Now I need you to understand that the Laplace of e to the t is equivalent to 1 over s minus a. The condition that should be satisfied is that s should be greater than a. Because if s is equal to a, we end up having 0, making it all undefined. Now let's try and prove this. By using the definition, or the first principle rather, as other people would term it, we'll say the S domain is equal to the integral from 0 to infinity of e to the minus st of the t domain f of t dt. In this case, we say that where the t domain f of t is equal to e to the at. So we have the S domain being equal to the integral from 0 to infinity of e to the minus st times e to the at dt. By applying in this property here, we have the S domain being equal to the integral from 0 to infinity of e to the minus st plus at dt. Applying some algebra on the power here, we'll have the S domain being equal to the integral of 0 to infinity of e to the minus, for pull out the negative, we'll have st minus at then dt. To integrate this, we'll apply u substitution. And under u substitution, we'll let u be equal to what is in the parenthesis. And that is st minus at. After doing this, the next thing we're supposed to do is to differentiate u with respect to t. So du over dt is now equal to s minus a. And by doing so, we then make dt the subject of the formula. And since dt is inversely related to s minus a, we'll have dt to be equal to du over s minus a. Now, remember that the S domain is equal to the integral from 0 to infinity of e. Remember, we have made a substitution of u, so we're having e to the minus u dt. We now know the value of dt, so we say the S domain f of s is equal to the integral from 0 to infinity of e to the minus u dt. In this case is du over s minus a. S minus a are constants, so if we pull them out, we'll have the S domain f of s being equal to 1 over s minus a of what we're having as the integral from 0 to infinity of e to the minus u du. Now, from the u substitution that we have, remember u is equal to st minus at. So if we want, we can say u is equal to t, then s minus a. Now with u simplified, we have our S domain as 1 over s minus a. By integrating this portion here, we'll have the negative of e to the minus u. The reason why it's negative is because the derivative of e to the something will be e to the something divided by the derivative of something, and the derivative of minus u is -1, making it all negative. So we have our limit from 0 to infinity. Bringing back the value of u, we have the s domain to be equal to 1 over s minus a of minus e to the value of u, which is minus t of s minus a from 0 to infinity. So we have the s domain being equal to 1 over s minus a. Then we have minus e to the upper limit, which is -infinity. We know negative infinity by s minus a will just be negative infinity. Then we have minus, then minus e to the minus of 0, which will just be 0 by s minus a. This will just be e to the 0. Now we need to know that e to the negative infinity is equal to 1 over e to the infinity. And this is bottom heavy, giving us 0. So the s domain is now equal to 1 over s minus a of this goes to 0. Then minus minus gives us a plus. E to the 0 is 1. Therefore, the s domain is now equal to 1 over s minus a. And this is proven. Alright, now let's move on to the fourth proof. The Laplace transform of cosh at. Now, you need to understand that the Laplace transform of cosh at, which is cos hyperbolic, is equal to s over s squared minus s squared. Now let's see how we can prove this. Now I need you to understand something. Cos hyperbolic of an argument 18 is equivalent to e to the 18 plus e to the minus 18, and all this is divided by what? 2. So in basic sense, we are finding the Laplace of this identity. This implies that what we're looking for the Laplace of cos hyperbolic of the argument 18 is just equivalent to the Laplace of its identity, which is e to the 18 plus e to the minus 18 divided by 2. Now, we can find the Laplace of the individual entity of the identity. What I'm trying to say is this, which is the Laplace of cosh 18, will be equivalent to the Laplace of e to the 18 divided by 2 plus e to the minus 18 divided by 2. By applying a certain property of Laplace, which is a linearity property, we can say that the Laplace of cosh 18 is 1 over 2 by pulling out the constant, then finding the Laplace of e to the 18, then applying the same thing on the other hand, plus 1 over 2, then the Laplace of e to the minus 18. The Laplace of cosh 18 will now be equal to 1 over 2. We know that the Laplace of e to the 18 is 1 over s minus a plus 1 over 2, the Laplace of e to the minus 18, the fact that it's a minus, that minus on the identity part of e to the 18 makes it a plus. So we have 1 over s plus a. The Laplace of cos hyperbolic at is now equal to, we can factor out the 1 over 2, and we'll have 1 over 2. Then we're having 1 over s minus a plus 1 over s plus a. by looking for the common denominator, we have the Laplace of cos hyperbolic at being equal to 1 over 2. The common denominator will just be the two factors here being multiplied together. And this will give us s squared minus s squared. On top, we'll have 1 multiplying s plus a, then plus 1 multiplying s minus a. This will give us 1 over 2 of the common denominator, which is s squared minus a squared, and we're having s plus a plus s minus a. This gives us 1 over 2. The common denominator maintains s squared minus s squared, and we know that in this case a and a cancels out, and it gives us 2s. Now the 2 here and the 2 on the s cancels out. Therefore, the Laplace of cos hyperbolic of at is now equivalent to s over s squared minus s squared. And this is now proven. Alright, now for the fifth proof, we have the Laplace of sine hyperbolic of the argument at. You need to know that the Laplace of sine hyperbolic of at is equal to a over s squared minus s squared. You need to know that the identity for sine hyperbolic of at is similar with the identity of cos hyperbolic of at. The only difference is that in this case, we're going to have a minus rather than a plus. So we'll have e to the at minus e to the minus at divided by 2. This implies that if we are applying a proof, then the Laplace of sine hyperbolic of at will be equal to the Laplace of e to the at minus e to the minus at over 2. And this can be broken down into the Laplace of e to the at over 2 minus, in this case, the Laplace of e to the minus at over 2. Therefore, the Laplace of sine hyperbolic of the argument at is equal to, if we factor out the constants, we have 1 over 2, then take the Laplace of e to the at, then minus 1 over 2, take the Laplace of e to the minus at. By doing so, the Laplace of sine hyperbolic of at will then be equal to 1 over 2. The Laplace of e to the at will be 1 over s minus a, then minus 1 over 2. The Laplace of e to the minus at will be 1 over s plus a. If we factor out 1 over 2, we'll have 1 over 2. Then we remain with 1 over s minus a, then minus 1 over s plus a. In a similar manner, the Laplace of sine hyperbolic of at will have 1 over 2, then the common denominator will be s squared minus s squared. This tells us that we'll have 1 times s plus a, then minus 1 times s minus a. If we continue simplifying this, we have 1 over 2, the common denominator, s squared minus s squared. When 1 multiplies everything here, we'll have s plus a. Negative 1 by s, that will be negative s. Negative 1 by negative a, that will be plus a. Therefore, the Laplace of sine hyperbolic of at is equivalent to 1 over 2. In this case, s cancels out with the s there, and you have a plus a, giving you 2a over s squared minus a squared. The 2 here cancels out with that 2, which tells us that the Laplace of sine hyperbolic of at is then equal to a over s squared minus s squared. And this is our proof. Alright, so in our 60th proof, we'll be finding the Laplace, of course, of the argument at t. Now, I need you to understand that the Laplace of cos of at is equal to s over s squared plus s squared. Now, let us find a way in which you can prove this. So let's look at the proof. When we say proof, remember that we're trying to use the definition of a Laplace to find what cos of the argument at is, and since it's s over s squared plus s squared, we want to prove that. Alright, let's begin. So the method that we're going to use here is integration by part, because we know that by definition, the s domain is equal to the integral from 0 to infinity of e to the minus st times the t domain dt. In this case, the t domain is cos at. This implies that the s domain is equal to the integral from 0 to infinity of e to the minus st cos of at dt. So the method we're going to use is by parts. So let us apply integration by parts. So we know that the s domain is equal to the integral from 0 to infinity of e to the minus st cos of at dt. So we'll let u, sorry about that, I'll write it cleanly. We'll let u be equal to e to the minus st, and we'll let dv be equal to cos of at dt. We'll find the derivative of u with respect to t, so du over dt is equal to minus s e to the minus st, and we can say that this can be put to say over 1, because in the end we want to make dt the subject of a formula. Now, since minus se to the minus st is inversely related with dt, what we can do is that we just make du the subject of formula since it's by part. So we say du is equal to minus se to the minus st dt. Then for dv, what we're going to do is to integrate both sides. Find the integral of dv, then also find the integral of cos of at dt. The integral of dv is v, since there's basically 1 there, and the integral of cos at dt is equal to sine of the argument at divided by a. Now, from the by part statement, we know that we have the integral of u dv being equal to u v minus the integral of v du. By substituting the values, we'll have the integral of e to the minus st, then dv, we have it as cos of at dt, and this is equal to e to the minus st. Then we have u as sine of at over a minus the integral of sine of at over a times what we're having as du, which is minus s e to the minus st over 1, then we can say dt. Now, if we clean this up, we have the integral of e to the minus st cos of at dt being equal to e to the minus st sine of at over a, and if we pull out all the constants we have here, we'll have minus with that minus gives us a plus, s over a. Then we have the integral of e to the minus st sine of at dt. Now, the integral of e to the minus st sine at is also another Laplace, which is just Laplace of sine at. So we're going to also integrate this by parts. So we're going to say that. Let us find the integral of e to the minus st sine of at dt. In a similar manner, we're going to apply the same thing. We're going to let u be equal to e to the minus st. dv, in this case, will be equal to sine of at dt. We'll differentiate u with respect to t. du over dt will be equal to minus se to the minus st. We'll make du the sort formula, and we have du being equal to minus se to the minus st dt. If we integrate both ends, integral of dv and the integral of sine of at dt, we'll have v being equal to the integral of sine will be minus cos of at over a. By plugging this back into the by part statement, which implies that the integral of u dv is equal to uv minus the integral of v du. By doing so, we'll have the integral of e to the minus st. Then we'll have times dv, which is sine of at dt, being equal to e to the minus st. Then v is minus cos of at over a, then minus the integral of minus cos of at over a. Then this is multiplied by du, which is equivalent to minus se to the minus st dt, like that. To apply further analysis, we need to understand that the integral of e to the minus st sine of at dt is basically just the Laplace of sine of at. With this said, it implies that the Laplace of sine of at is equal to e to the minus st by minus cos of at over a. And if we take the limits from 0 to infinity, we'll have minus s over a, then the integral from 0 to infinity of e to the minus st cos of at dt. If we apply further analysis, we'll have the Laplace of sine of at being equal to, if we substitute the limits, we'll have e to the minus infinity, let's just put this over 1 for now, times minus cos of infinity, and this will be over a, and this will be minus e to the 0 times minus cos of 0 over a, like that. And we'll have minus s over a, then the integral from 0 to infinity of e to the minus st cos of at dt. Therefore, the Laplace of sine of at is equal to, we know this will lead to 0, but this will give us 1 over a. So we have 1 over a minus s over a. Now, if you look at this here, this is just basically the Laplace of cos at. Now, with this in mind, it implies that from what we had earlier on, before we computed our data, we had the Laplace of cos of at, which is s over a, then the integral from 0 to infinity of e to the minus st sine of at dt. In case you don't remember, we're talking about this portion here. Now, with that in mind, we can now say that the Laplace of cos of at is equal to s over a, the Laplace of sine of at dt. This tells us that the Laplace of cos of at is equal to s over a, then the Laplace of sine at, which is what we have here found, will be 1 over a minus s over a, the Laplace of cos of at, like that. If we apply further algebra, we'll have the Laplace of cos of at being equal to, if we multiply this, s over a times 1 over a, this will be s over a squared. Then s over a times s over a, that will be s squared over s squared of the Laplace of cos of at. Now, if we take this on the other side, we'll have 1 Laplace of cos at plus, since it was a minus, s squared over s squared, the Laplace of cos at, then this is all equal to s over s squared. If we factor out the Laplace of cos, we'll have the Laplace of cos at will remain with 1 over 1 plus s squared over s squared, and this is equal to s over s squared. Now, if we do up a side data, say 1 over 1 plus s squared over s squared, if you look for a common denominator, we have s squared, then this would be basically s squared plus s squared. This tells us that on the left-hand side, we have the Laplace of cos at having s squared plus s squared over s squared. And this is equal to s over a squared. Now, to find the Laplace of cos at, we need to multiply the entire equation by the inverse of this, which is s squared over s squared plus s squared, which will cancel this, and we just remain with the Laplace of cos of at being equal to s times s squared. If you want, you can just say s, then s squared in parenthesis, then s squared again times s squared plus s squared. We know that the s squared and the s squared will cancel out, telling you to say that the Laplace of cos of at is equal to s over s squared plus s squared. And this has been proven. We're going to look at the Laplace of sine of the argument at. Now, I need you to understand that the Laplace of the sine argument of at is equal to a over s squared plus s squared. Now, how can we prove this? Now, recall from our previous proof, of course, since the Laplace of cos of the argument at was equal to s over a, the Laplace of sine of the argument at. What we can do here is basically make sine, the Laplace of sine at, the substitute formula by multiplying the entire equation by the reciprocal of these constants. So we're going to say a over s, and we'll have the Laplace of sine at to be equal to a over s times the Laplace of cos the argument at, like that. Now, the Laplace of cos at is equal to s over s squared plus s squared. This implies that the Laplace of sine at is equal to a over s times s over a squared plus s squared. The s cancels out with the s, and you have your plus of sine at being equal to a over a squared plus s squared. And you have your proof. Alright, thanks for watching. If you have any queries, you can reach out to me on WhatsApp on the line +260 77 149 5252. Remember, slow progress is better than no progress. Unless you're just before becoming a statistic, let's try and push for that A+.